To week 4 of the Qubit x Qubit lab. I guess I'll kind of get started, and we'll go through Canvas and everything while people trickle on, because I think we're at about half capacity now, unless there's been a big drop off in the past couple weeks. Yeah, so today we're going to go through kind of the same things as we usually do with announcements. Then we're going to do questions from last week, and then lab content, which this week is going to be on matrix multiplication and applications into how these are used for quantum computers and quantum gates. So mentioned last week, but we do have office hours virtually on Friday all day. I guess possibly all night, depending on where you are, but hopefully part of the day at least. And that's 8 a.m. to 8 p.m. EST, or UTC -5. And that's being run by a lot of very helpful people in the course that are students like you guys, but are maybe knowledgeable on some area. They've all been kind of checked to make sure that they have some knowledge at the back of the course. And oh yeah, also if you have not already, so this is the Canvas quiz for this week. I'd like to note that in the bottom right corner, there is the number on every single slide. So if you're coming on later, or if you don't do it now, you can always check the bottom of the slide to find the passcode for the attendance quiz. And this is through Canvas, like last week and I guess the week before now. And this is the question that you'll be asked, trying to get the magnitude, the specter. As a reminder, that's if the vector is x, that's this. So you guys can go and do that now. And if anyone wants the answer to this, I can pop back later, but I'll let people do this now. Is anyone else having issues with the attendance quiz passcode not working? I've seen one message about that. Okay, so hopefully just try putting it in again if it doesn't work the first time, and then hopefully it will work. Okay, so we're also going to do pre-lab Zoom feedback since I can't see your Canvas feedback. And I'll start the poll for that now. Just as usual, 1 means you did not understand anything from this week's lecture. 5 means you already knew all of it, or you thought it was very easy. And then 4 means you understood it, but it wasn't like too slow or anything. Okay, so I'm getting mostly 4s and then some 3s and 5s. So that's good to know. I'll try to keep to that for this week. And as the first thing, we don't have any prepared questions from last week, but does anyone have any questions they'd like to ask from last week's content, which was on vector notation and kind of vector addition, imaginary numbers, all of that. Any questions on that, or I guess applications to quantum computing? We will be going into that in a lot more detail this week. So I might stop you if you're asking too much about gates, because we're going to be giving some explicit examples of that later. Yeah, I'll let everyone think of questions. And it doesn't have to be super related, as long as it's like tangential, I'll take it. I'll give like 30 more seconds to find questions. Okay, I've gotten a question. Thank you, Elon, for submitting your query. I appreciate the questions from everyone. So this question is, why do gates have to be reversible? Why can't we lose information? So in a quantum computer, we are dealing with the quantum state of the system. And so a lot of times you'll see these represented as energy level diagrams. So let's say this is the 0 state, this is the 1 state. And these are all energies. And when you perform an operation that's not reversible, you have to be getting rid of some of the information, some of the energy. So if you get rid of some of the energy of this state, then maybe instead of going from the 0 state to the 1 state, you're now in like some other state that you're not sure what that is, or maybe it's not even normally there's not even an available state there. So you just lost some energy going out into space, and now you have that loss as a part of your states, and because of that, it's what we represent this as on the block sphere. A lot of times is that we no longer have a pure state. We have what's called a mixed state. So we've lost some probability of being in each of these known states. And I could go into more detail, but I don't know if there's a lot of background for this. So if that made sense and you always want more information, that I can kind of give a more explicit example of that. But the rough idea is just that every state that you're in, or every particle that you're looking at, should add to a probability 1 of being in a variety of known states. And there's certain states that you want it to be in. And if you have loss, then you can be having some of this information go into unintended states. And that's not what you want. So that's the rough overview. I've gotten a question on the unit vector. We'll be going into unit vectors momentarily in lab today. So if there aren't any more questions, then I will go into the lab content, and feel free to ask questions. We'll have like stop points throughout the lab anyway. Okay, so today we're going to be learning how to compare vectors, including normalizing them and looking at unit vectors. So normalization is comparing the magnitude of a vector. Unit vectors are comparing the direction of a vector. And then we're going to go into vector inner products, which I know is covered in lecture, but we're going to give more examples. And then we're going to go into matrix notation and multiplication and how that applies to quantum computing and these quantum gates that I know you're all very excited to learn more about. Okay, so the next couple of slides are just, if they look familiar, they are a brief review from last week. So here's here's a schematic of our quantum computer. We have our quantum bits, which are 0 and 1, which is these vectors. These conveniently point on the block sphere to the 0 state and the 1 state. And these states can be in a superposition of, or your overall quantum state can be in a superposition of these two states. So this is our square root 2, 0 plus 1 state is along the equator of the block sphere. And that's in comparison to our classical states, which don't have any phase associated with them and are just a 0 or a 1 by themselves. They're just a scalar value. So the important thing is just that these are vectors and they can be added together in this vector basis. So we have a bit on that. Again, this is the difference between the vectors and the scalars, is you have just a number here, while you have 2 or can be more numbers. And one thing that I'd like to note, I guess, is that the number of states you can possibly have is the size of this vector. And we'll go into that a little bit more later. But because we can have 2 states, our vector is of size 2. If we could have 4 states, like if we could have 0, 1, 0, 1, then we'd need to have something that can have 4 states, which corresponds to 2 particles or 2 qubits. So that's just a brief little extension. So now one thing that we might want to do is compare different vectors. Like we showed in the block sphere, maybe we have two different states and we want to compare how much these states overlap. Does anyone have any ideas for how we might be able to do that? And feel free to put in the chat. So we have this vector u and this vector v, and you have them drawn out. We want to compare what these two vectors are. So I've gotten a lot of good answers. I've gotten some about the angle, about the magnitude, about the inner product. So these are all very good answers. Thank you to Angela and Carmen, Megana, Audrey for your suggestions. Yes, so what we want to do is we want to compare these two vectors, and we're going to do it step by step. So we're going to take the magnitude of the two vectors first. So the way that we take the magnitude, to remind you, we did cover this last week, is we take the square root of ux squared plus uy squared, which in this case is square root of 3 squared plus 2 squared. And that gives us square root 13. And then similarly, we can take the square root of v, or we can take the magnitude of v, exact same way. This gives us 2 squared plus 1 squared, just square root of 5. And so we can say that u is bigger than v based on this magnitude. But so Clark, you have made a very good point. Yes, u is backwards on the slide. We did not catch that. Yeah, so that the way it's written as is, u would actually be over here. And I'm just going to relabel u here rather than doing anything. See if I can get rid of this. Haha, great. That's our new u. Yeah, great. So that's one way we could compare the vectors. We can compare their magnitude, and we have a kind of written out version of what we just did. We can also instead compare the directions of these two. So instead of taking the, and all these are going to be wrong with friction, I'm just going to fix this, I guess, because it might be a little quicker. Oop. Good enough. I'm going to make this the correct value. Okay. So yeah, if we want to instead compare the directions of these two vectors, you can see that you could define the angle of each from the x-axis. But to make this a little bit, or to make this easier to represent in vector notation, we're going to just normalize the two vectors by their magnitude. So we took our value, we remember our normalization, or we remember our magnitude from before. This was square root of 13, and this was square root of 5. And so to get our normalized value for our unit vector, we want to just divide what we had before. Sorry. And so our resulting value would be, I'm not going to work this out just because this would be, it's going to get some like random decimal that's not going to be super intuitive. So we can represent this like so. And similarly for v, where you can just divide through with these values. Here we are. Okay. So we can draw this out on the diagram here, where again, we do have these swapped consistently. It's just, there we are. And so you can draw these out, and now both of these lengths are now 1. So this this normalization allows us to compare the exact values or the exact directions of these two vectors when they are both of length 1. And we're going to kind of extend this into the concept of the inner product for comparing kind of both of these at once, this direction and this value. So now we can take the angle of both of these values or the angle of both of these vectors by looking at this formula, which we covered, I guess, 2 weeks ago now, where the angle, which is always again defined from the x-axis, is equal to the tangent of the y coordinate, I guess, or the, yeah, like this. If we take this as b sub x and this is b sub y, just to note, because we didn't actually know that notation yet this week. We are y coordinate over x coordinate. We can get the angle out for each of these, and this is not going to give us a clean value that you can easily calculate. If you have a calculator on hand, you can. But you can easily compare the two angles by looking at this. And if we have a normalized result, we already don't have to do too much. We don't have to do much to compare these angles. So that's, I guess, where we're at with that. We're going to go into inner products to get these more, to make this a little bit more explicit. But does anyone have questions on that so far? And I've gotten a question actually for why dividing by the magnitude results in a magnitude of 1. And I've also been asked to go back to the previous slide. So because the magnitude is equal to the magnitude, I guess, you divide by the magnitude, you get magnitude 1. So the length of any vector is always going to be equal to the magnitude that we've defined. So this ux squared plus uy squared is always going to be the magnitude. So if you divide your vector by the magnitude, your vector's magnitude, or so the magnitude of this, is now going to be 1. And that's because you've already taken pretty much what you're doing when you just take the magnitude. I guess it's if you haven't seen this before, it's not totally intuitive. But when we take this bottom value is already a scalar. So this extra magnitude taking doesn't do anything, but we're taking now the magnitude of the top, and so we end up with the magnitude of the top over the magnitude of the bottom, which is just 1. So I've gotten a question about the normalization. And so the tangent, I guess, is it needs to be defined from, or is only defined from 0 to 1. So we need to have a value that is in that range in order to get the result out that we expect. Because that's how the function, I guess, is defined. Like we don't want to have random numbers like that are very large. We can't just plug that in as easily. So I've got another question about why you have to make magnitude 1 to compare the angles. You don't necessarily have to, I guess, but it's just a little bit simpler because when you are I guess because when you're doing all this mathematics, it's a lot easier when everything is normalized because all these functions are defined from 0 to 1, or I guess -1 to 1. So in this way, it's a lot easier to complete this math. Specifically, when we're doing quantum computing, everything is normalized to 1, and that's because, I guess I'll write it out, the probability of all of your quantum states is equal to 1. I guess I don't know how the best way is to write this, but if you add up all of your quantum states, so you have a sum over maybe like state 1, or I'll give it a probability. So we'll say we got probability 1 times state 1 plus probability 2 times state 2, etc. This, and we can say this is I. This is always going to be equal to 1 because the probability of everything together is always going to be 1. Like there's always likelihood of 1 of something happening because we know that we have some state. You can't, if we're looking at it, we've already assumed that there's not nothing there. So anything that we can be looking at must have some defined state, and that's always going to be equal to 1. So that's I guess a tangential justification for why you might want to normalize things. Okay, great. So now I'm going to move on to the inner product. If you have more questions, we can also go back later. So this is a definition of the inner product. This notation is the same as doing, oh, that's a really ugly B, sorry guys. Same as this kind of centered dot. That's the exact same. The result of this is this here is the conjugate transpose. And the conjugate we covered last week, but the conjugate is equal to this vector with a star. And so if your vector has an imaginary part and a real part, let's say real V minus imaginary V times I. I've written things too close together. Okay, yeah, so this star means that we've inverted the imaginary part of V. So if you were writing V without the star on it, if you're not used to this notation, this real, like this just means the real part, and we would add instead I times the imaginary part of V. And if you're wondering why we have if you're wondering why we have this I here, it's because when we take the imaginary part, we're taking just the value of the imaginary part. So if you remember our matrices or our vectors from last week, where we took this, like maybe this is the real part, this is the imaginary part. There's not an I there. It's just the value that is the imaginary part of the value. And then the transpose is something I don't think we've explicitly covered. It's normally, let me go and just like shoot an arrow down here. The transpose is if we have, or let me define V first, like let's give an example of V. If our V is Vx, Vy, V transpose is instead Vx, Vy. So we've kind of turned it on its side. And so when we take the conjugate transpose, we take the complex conjugate of all of the values, and then we also transpose the matrix. And this is just a vector discussion of this, but you can also do this with a matrix. So if you had a square matrix maybe, where you have B11, B21, B12, B22, and we take the transpose of it, we keep the on diagonals the same. So the on diagonals being these guys, and the off diagonals will swap. So now instead, we have B12, B21, B22. So we just swap those two values. And I'm just going to annotate these for the future. And sorry if my writing is too messy that you guys can't read it super well. I can slow down and I'll slow down the lecture a bit, but it will make it easier to read. So just let me know if it's too messy. Okay, so that's the definition of this, and that's what we see here. This kind of assumes that we have, or that we know what we're doing multiplying these two vectors. So in general, vector multiplication assumes that the dimensionality of one vector or one matrix must be like appropriate for multiplying the other matrix. I have it written out, I think, or I have it written out in a couple slides. But you need to have the same dimensionality if you have, for example, like an n by m matrix. You need your other matrix to be an m by, can be whatever you want, be m by p, but these must be the same. This is just the definition. This can be treated a lot more simply. You don't need to have this very general equation for it, but this is the generalized form. And we'll go into more examples. So now we're going to take the inner product of a value. So this is a simplified version where we're now in a basis with only two states. That's pretty much the entire course. We're going to only be dealing with two states the entire time. So if you don't get the generalized form, you can just look at this formula. This is all you need, because if you only have two states, then you only need to deal with this. So I guess with this formula, I want to open it up to see if you guys can calculate what this u dot v would be, or this inner product of u and v is. So I'll give a couple seconds to do that. It's not too large of an equation, so hopefully it doesn't take too long. Well, if you guys can't quite figure it out, I'll also just work through it. So again, we can, instead of denoting these as like u sub x and u sub y, we could take this as u sub 1 and u sub 2, which is what we've done on this slide. Sorry, the notation isn't always consistent, but it's all equivalent. So we can take this inner product to now be the first values multiplied together, so that is 3 times 2 plus the second value, which is 2 times 1, and that just gives us 8. So that's all we've done. We've taken, this is how much these two vectors, I guess, overlap. It's a kind of a measure of how much you can project one onto the other. And you can get the scalar value out of all these. So a lot of times it's also called like a scalar product of the two. So you can also take something like this, where we now have vectors facing in two different directions. So we can take the exact same procedure, where this is our u1, this is our v1, this is our u2, v2. Sorry that my 1s and 2s look really similar. what can you do? So now we end up with -6 plus +6 for these two. And so that actually results in nothing. And you can kind of see this or have guessed that maybe this would be the case because the angle between these two is 90 degrees. So when two vectors are orthogonal, like all of our bases that we've been dealing with, we discussed previously, are orthogonal. That means that their inner product is going to be 0. And you've probably seen this if we have something facing along x, something facing along y, the inner product of those two is always 0. And that's a kind of a definition of this inner product, although you can also work it out for any given number of examples. You'll always end up with that. And I guess while we're, yeah, I guess now we can move on to questions on this. If you guys have any, this can also be generalized to more angles. I thought I had it written down, but I don't want to get it wrong. Oh, the chat is disabled? Oh no. Kim, would it be possible to get the chat enabled?
Yeah, it should be enabled. Okay.
Okay, great. Cool. Okay, so yeah, if you guys have any questions on the content so far, we can go through that now. Yeah, so I guess we didn't do the definition, and I am like mildly rusty on these inner products. So hopefully I will get this right. But we can also take these inner products as the magnitude of the two vectors times the cosine of the angle between them. So this, if any of you in this course have covered this before, let me know if I mess something up here, but I believe I have it right. I have not reviewed this. It's the cosine of the angle between the two. So this will result in, if this is projected closely together. Oh, good. Yay. Thank you all for confirming. I should have looked this up beforehand, but I was like, oh, I'm sure I remember it. Shockingly, I've remembered something from like 10 years ago. I have computers to do this normally. That's what I'd really recommend, is just don't do inner products. Not even once, just have your computer do it for you. So this will also give you the projection. It's a little bit more intuitive, I guess. So if we have, this is square root of 5, this is square root 13, that'll give us, how do I do math? 5, 15, 65 times the cosine of the angle between them. So if you are directly on each other, then this would just give you the square root of 65. But because we're slightly off, which, yeah, because we're not quite on top of each other, we end up with a smaller value. So that is right. Okay. Yeah. So this this equation is also just kind of definitional for how the inner product works. You can kind of intuitively see it, I guess, by looking at your trigonometric identities. If you instead defined one vector as being at angle 0, so that's kind of what I've drawn out. If we take this right here, this pointing along B, to be angle equal to 0 degrees, then whatever the angle up from that is going to be your is going to be your sine. So this distance right here would be your sine theta, and this distance right here would be your cosine theta. So the projection of one value on the other is going to be and so you could take this, I guess, to be either in some sense, but the way that we've defined our inner product is that it is always the cosine of this. I guess you could take it to be, well, I don't know why you can't take it to be the sine, because it should be, it is just like kind of the orthogonality condition. I think there is a equation for that. But this will give you some value from 0 to 1, because your vectors can be anywhere from fully in opposite directions to fully in the same direction. So if cosine of theta is 0, that means you're at pi over 2 or 90 degrees. If cosine of theta is 1, that means you're at some multiple of 0 or pi. And that will result in these vectors just simply adding together. So that's how you can get a much larger value out. I've also gotten a question about if the vector is an element of complex numbers, if one coordinate has to be real. So I'm going to go to the empty slide just for the sake of not having it be confusing. So we previously defined our basis, I guess, as this is 1 and this is I when we were looking at these, or let's make that a little bit more clear. We defined our basis as 1, 0 and 0, I when we were dealing with real and imaginary numbers. So this is our real vector, and this is our imaginary vector. We don't have, so in general, and kind of hinted at by us having this conjugate operation we can do, this is not always the case. We could very easily have something that just points. We could have our basis for our qubits, where this is 1, 0, 0, 1, and we could easily have, I guess, 10 plus 3i times 1, 0 plus 5 minus 6i times 0, 1. This is a completely valid representation. This would end up with 10 plus 3i, 5 minus 6i as our vector. That's totally allowed. This was just a basis choice. And that's what we're going to deal with a lot of times. And this is, you don't always have to have things be defined, or you don't have to always have things be defined in the same basis. So these numbers that we've now written out, like they can be described as a vector or as a scalar. We could also choose to instead we can have this still, I guess, 2D matrix. We could have this as 10, 3, and 5 minus 6 within that. If we wanted to have this basis within our basis, like there's a lot of different equivalent descriptors. Pretty much what we've done here is we've taken an extra degree of freedom. And this degree of freedom, typically we do not normally take this imaginary number to be it's not an extra state, it's a property of a state. So we discussed previously that we can have a phase on a qubit state. This is our phase, and this is what always eats up the imaginary part of our state value. So when we are describing our qubit state, we still would normally put this whole phase as, I guess it can be as a relative phase between the two states, or you could put it in the value of the state, but it's not an extra state in of itself. So it'd be a bit confusing, I guess, to write it out like this a lot of times, this right here, because the we want to make clear that we don't have 4 possible states. We just have 2 components describing each state. It'd be like if you're trying to describe 2 vectors, I guess, in a matrix for some reason, or like you have a vector of vectors, which a lot of times a computer will hold a vector of vectors. So we could have our x hat plus y hat plus z hat as a location on a computer as a vector that's located somehow like that. And then we could have, I guess I can put some random numbers down. This is x minus y plus z. This is a totally valid, and let me put it in square brackets just to be clear. This is just a vector. You can represent anything as a vector, but how complicated the state that you're looking at is can vary. And so this is an acceptable way of describing it, but it's not necessarily as clear, I guess. Yeah. So I've got a question from Angela about how complex numbers are scalar if they have a sense of direction and can be represented as a vector. I guess they are always a vector. The magnitude of the complex number is a scalar. And so a lot of times we'll just multiply it by this I, which just informs you that it is along the imaginary axis. But it's not like you can't get rid of the I and have it be still representing the same number. I think it's really just a matter of we don't have like imaginary numbers and real numbers and like blob numbers as like a third option. We only have these 2. So we have this extra symbol that we add to it to say that it's on a different axis. And we don't really have to deal with that much more than that. But our representation, I guess, doesn't inherently assume that everything is real unless described otherwise. So it is a little bit of like notational confusion, I guess. I see how this has actually been a really good discussion. I'm glad that you guys have asked all these questions. This is a very, very good point, that it is a bit weird that we can describe these imaginary numbers both as locations on a vector. I guess you couldn't describe it easily in a coordinate system unless you have an explicit descriptor of how these work. A lot of times you will take any of these variables as having their own location on their own axis. And that makes it a lot easier to represent. But yes, it is a good point. This is notationally a bit confusing. Yeah, okay. So I'm going to try to get through the rest of the material next 15 minutes because I've kind of rambled more than I should have. But it's a really good question, so I'm glad you all asked. So we're back to our schematic of a quantum computer. And now what we want to do is we want to actually look at how we can take the gates in this computer, like an X gate or a Y gate or a Z gate or a Hadamard gate, to take our qubit state. Maybe we're in state 0, 1, and we want to get some other state out. We just want to like flip the bit. And we're going to discuss how we do that with using the ability to transform vectors. So if we have our state U represented here just as this vector, and we want to transform it to U2. Can you guys guess, I guess, how we can do it? I think I've probably said it already a couple of times, but do you remember how you might want to take one vector to another vector? Yes, so I've gotten some good suggestions. I appreciate all of these thoughts. These are a very good point. So the way we're going to do it is by a matrix or a gate. If we multiply a matrix or a vector by a scalar, which I appreciate that some people did suggest that, is that we haven't actually mentioned or shown explicitly what happens if we maybe multiply U1 times 2. We just get the same direction, but twice the magnitude. So our U1 would be here. That is completely unreadable. So if we are trying to keep everything normalized, we will never want to multiply a vector or a state by a scalar because that will just change the magnitude of it. It won't actually change the direction or our representation of the state. But that is something that, like, functionally, that's kind of what's happening when you have loss happen. Like you've lost a little bit of that state, and now it's like randomly located. So that's a very good point. So do this transformation. We're going to use a matrix. And so we have our matrix notation. So for those that are less familiar, I know most of you have probably seen a matrix, but for those who haven't, we have our vector where we just have our dimensionality 2 here, and we have 1 here. And this, we're going to have the same dimensionality for both. We want to always have a square matrix for these transformations. So this is 2, so this also has to be 2. And this is how we're going to perform different rotations on our qubits. And in general, like a lot of descriptors will call these matrix transformations rotations. If everything's normalized, that's all it should be, is a rotation. It should not be changing the magnitude of anything. So here is a general form of how we use these matrices to transform vectors. Again, like I said earlier, we need to make sure that we have these dimensions match. So if we have a matrix with n columns and m rows, we need to be multiplying that by a vector of dimension m to get something reasonable out. And this is, again, this is generalized to not just square matrices, although for the remainder of this course, I believe we will only be discussing square matrices. So if you wanted to, if you're actually forming a quantum operation, this would always be m by m. So this is a square matrix, which means that it has the same dimensionality, and then we'd multiply like on both axes. And then we'd multiply that by our qubit vector, which is of whatever dimension we're dealing with. And then in general with these qubit states, we are in, a lot of times we actually define qubits as two-level systems. We call them two-level systems. Any two-level system can be a qubit, you might say. So this will always be, in this course, a 2 by 2 matrix times a 2 by 1 state. I guess we might have some 2 qubit states that we discuss at some point, or we probably will. I don't know if they'll be this semester, but occasionally we might have a 4 by 4 times a 4 by 1. But that's just a matter of the number of qubits that you're dealing with, and we pretty much never, or very infrequently, do people discuss interactions between more than 2 qubits, because it rapidly becomes computationally annoying to deal with. And most of these kind of intuitive and basic operations are just done with 2 qubits. You can have a universal gate stat with just 2 qubit operations. You don't need 3 qubit operations or anything. So now we're going to go into how we use these matrices to transform the vectors from one state to another. So this A here is a matrix. You can see it's in bold, which tells us it's a matrix in this notation. And it has it's a 2 by 2 matrix, like we discussed previously. And then we have our input, which is our 2 by 1 vector. And then we'll end up with the exact same kind of multiplication as we saw earlier with these inner products, except now instead of multiplying, we can treat each, I guess, row of this as taking the inner product of this row with this vector, and that gives you this row. And then we have the inner product of this row with the same vector again, and that gives you this. So it's the exact same multiplication. This is how we always do matrix multiplication. This is just the general definition for it. That's how we can get these values out. So now we're going to give an example. And this actually, despite how boring and simple it looks, happens to be a very important quantum gate. So does anyone know what the answer to this matrix, this 0, 1, 1, 0, times our one state is? And you can calculate it. So I want the vector notation version, but if anyone who does know the gate is also welcome to mention it. I've gotten thank you to Fadi and Thomas and Dennis and Eric for your responses. Yes, this will just give us a 0, 1. And this is in fact an X gate. Yeah, you found your first quantum gate, at least in lab. It's really simple. It literally is just a couple zeros and a couple ones. And you think that seems so, I guess, boring, but that's all of quantum computing is just built off of these really simple, generally like invertible, reversible operations that do very simple things to two states. And I guess if, so we're going to give a couple more examples. I've gotten a question from Audrey about why it isn't 1, 0. So if you don't find this super intuitive for how to do these multiplications, a lot of times I like to just imagine the vector and imagine picking it up and rotating it and putting it on top and putting it here, and then be like, okay, I got this 1 times this 0, and then go through that way just to make it more clear. It's all kind of how you find it most intuitive to do the mathematics. But this is just definitional for the multiplication. Thank you all for your questions, though. It's always helpful because I know a lot of people, we go through this a lot very quickly. So I know a lot of people who haven't seen the material before may have questions and may not be able to pick it up with how quickly we're going through. So it's really good to make sure that I'm going slowly enough. Okay, so now we have a bunch of slides here, but this is just our X gate shown diagrammatically. And it just gives you, it inverts the state. So this is our 0 state. Oh, I am still in eraser mode. This is our 0 state, and this is our 1 state. And that's all this does. So now we're going to give one more example of a gate. Can anyone do the calculation for this? And again, it's just two multiplications you need to do, I guess, or 4 multiplications, 2 additions. Addition, yeah. No, 2 How do I do math? Yes, 4 multiplications, 2 additions. I'll get it eventually. So guys can think through that. Thank you, Clark, for the quote. Okay, I work on physics for the most part, not on these more mathematical descriptors. So I don't find it interesting until there's some loss or some interaction with other states for the most part. That's just me. I'm biased. But I think it's not boring, it's just very simple. And I think people build it up like it's all this magic, and it's literally just a 2x2 matrix. And the only options are zeros and ones. So it's what you have such a tiny space of options. But it is really cool how much you can do with that. So thank you all for your responses. Yes, so we'll just do the multiplication. So this gives us our square root 2 times 0 times 1 is 0. 1 times 1 is 1. This gives us 1 over root 2 on top. And then same thing on the bottom, but with the negative sign. And so this is often called, or is called, a Hadamard gate. And this gives us, which you may have noticed, an equal superposition of the two states, plus technically a phase on this. So this minus sign kind of tells us that we have an EI pi happening, because that'll give you a -1. And so this, I guess, is an equal superposition pointing along the -x direction, or yeah. And again, this note here is due to the normalization. Whenever you see this square root 2, this is how you normalize any state, I guess, that any like two qubit state can be normalized at the square root 2. So yeah, great. So now I'm going to go through, just show you this kind of diagrammatic example, or diagrammatic like picture of it. And the important takeaways, I guess, this whole section is that our qubits can always be represented as a vector, our gates can always be represented as a matrix, and all you do is just multiply the matrix with the vector. And it's extra simple because the only options for your numbers are 0, 1, and -1, plus like times the normalization constant. And the only sizes we're going to be dealing with for the most part are two state matrices, because again, all these qubits are just two level systems, or two state systems. If you're dealing with 2 qubits, all we've done is move it up to a 4 state system, or a 4x4 matrix. So I'm going to take questions now, and then also launch the poll. Actually, Kim, would you mind launching the poll for the post-lab Zoom feedback? I just want to know how you guys felt about this, and I think we have a lot of optional content that you guys can feel free to stay on for later, but no need to stay on.
You want me to launch now?
What?
Do you want me to launch now?
Oh, yes, please. Thanks. I don't know how to launch polls except for the first time. Okay, great. This is just how much you understood of this week's lab section, not the lecture. And then I'll adjust next week. And if everyone's like, oh, this is so slow and boring this week, next week you should tell us more, and I can do that. Yeah, so this section is recorded, or like you guys aren't, but my lecture is. So this should be posted to watch later. It's part of why I have to go through all the material, but I was too slow this week, I guess. Yeah. And then I've gotten a question about normalizing a 4-qubit state. So yeah, generally the normalization is you want everything to add up to 1 in the end. So if you had a vector like this, where they're all 1s, and you want to normalize this, so let's say we take the magnitude of this. We want to take the square root of 1 squared plus 1 squared plus 1 squared plus 1 squared. This is just how you normalize anything. So if we're doing a 4-qubit, like this is a 2-qubit state, or a 4-level system, because we now can have combinations of the 2 qubits. This will give us a square root 4. So that does mean that whenever you're representing a state like this, if you want it to be normalized, our normalized state will be 1 over root 4, 1, 1, 1, 1. And that's our normalized state. Great. Okay. So we have a lot more material, but again, no need to. Hopefully I'll try to blast through it pretty quickly. And this is all just going to be a little bit more on matrix multiplication and inverting matrices. Great. Love you guys answering each of the questions. Thank you, Rohan and Elon, for your question and your answer. Yes, whenever you normalize, you just make the magnitude equal to 1. Great. So we're going to go through how we can then add these gates together or perform multiple gates, what happens when we perform multiple gates on a qubit. So that's this last line. So we've done these first three already. So congratulations, you've learned how to perform gates on qubits, but now we're going to do multiple gates. So now we're going to look at multiplying larger matrices together, or two matrices together rather than a matrix and a vector. So again, this is the same notation here where we need these m's to be the same in all of what we're going to be doing today, and a lot of times what we're going to be doing later on in the course is just going to be the 2 by 2 multiplied by a 2 by 2. So that's all we need to deal with. So here is a 2 by 2 matrix multiplied together. You can see that all we do is we just multiply the first vector by the first column, and that will give us this. And then we do the same thing for, the first row by the first column, and then the second row by the first column gives us here, etc., all the way through to get this full matrix multiplication. This, I guess you can treat it as almost like rotating the matrix rather than rotating a vector, if you prefer to think of it that way. So I'm going to give an example of these are the two matrices we had earlier. And this is our X gate. This is our Hadamard. I'm going to include our normalization in my little squiggle. Does anyone know the answer to what these two multiplied together is going to give us? This is going to be 4 8 operations. Yeah. So I've got a question from William. If quantum gates just multiplying matrices together, pretty much. Like, I mean, quantum gates are generally like multiplying a matrix by a vector, but if you want to just pretend like you're performing both gates at once rather than doing, okay, I'm going to multiply my quantum state by or have a gate operate on my quantum state, and then I'm going to get a state out, and then I'm going to operate on that state by another gate. You can think of it that way, or you could just think of the two gates kind of conglomerating together, and then you've just multiplied the two gates or the two matrices for the gates together, and then you can just directly operate that on the state and get your resulting state out. So I'll just go through this math for everyone. So we can do is we want to take this 1 time and this 1. We have 1 times 0 is 0. 1 times 1 is 1. So we get a 1 here. And I'm going to keep the normalization outside just to make it look a little cleaner, because we're going to get 1s everywhere. I don't know if you guys knew that, but we are. And then we get a 1 times this. We have this one by this one by this 0. Again, it's just a 1 again. Do it again with this 1 by the 0. And this -1 by this 1 gives us a -1. And then this 1 by this 1, this -1 by this 0 gives us 1. And then we can normalize with root 2. And so this isn't, I guess, like a commonly thought of quantum gate, but we could multiply this by a vector if we want to see what it does, maybe on our 0 state, or what's our 1 state? We'll take our 1 state. Let's see what it does to our 1 state. So we can multiply this through, and this will give us a -1 and a 1 times 1 over root 2. And so this has put us into an equal superposition that is the exact opposite of the other equal superposition we had. So previously, if you remember with the other Hadamard, we had our, I guess we put that on a 0 state, didn't we? Well, I think this will give us the same thing in the end. But yeah, we've pretty much now have a pi phase up here on the zeros, on the first row instead. But we could also kind of shift everything around and rotate it. We can, in general, that's called changing the frame that we're looking at it in. Obviously, when we have a sphere like this, it is spherically symmetric. So we could just rotate it 90 degrees and it would look exactly the same. If you ever want to change the representation of what you have, you could easily do that depending on where you're starting and where you're ending up. But that's a little bit more complicated of a topic. Yeah, so now we have this going through and doing it. And this gives us the same value we got out. This is just the results of this, this operation. So these are the exact same thing. This is the picture version. This is the mathematics version. This is what you'll get out when you do a Hadamard and then an X-gate. Always. And the one thing to note is that when we're showing it in a circuit, we show the Hadamard first and the X second. When we're multiplying matrices, you always multiply from right to left rather than going from left to right. So we have our vector here, and then we have our Hadamard, and then we have our X. This is our state. And so we make sure that we always want to invert the direction that we do these things. Speaking of inversion, we're going to very quickly go through matrix inversion now. So now if we end up, this is our final state. And we want to know what initial state we were in that resulted in this, this final state. Does anyone have any ideas for how you might do that? Here's a picture, or here's a mathematics version of it. So we could also treat it like this equation is completely equivalent to this equation. Great, so yeah, thank you for everyone who's suggested. Thank you, Audrey and Fadi and Eric. Yes, so the rough idea is that we do want to divide by the matrix, and what we're going to do that, I have a bunch of slides that I don't know why I make so many slides. I should make fewer slides and just write on them. But yeah, the idea is we want to do this division, but when we have a matrix, we can't just divide a vector by a matrix. We don't have a definition for how that works. So instead, we take the inverse of the matrix and I guess left multiply the vector by that. So you can show that these two equations are equivalent because we know that our matrix inverse times our matrix has to be equal to an identity matrix, which is represented like this, and that's a 1 or 2D identity matrix. It just has ones on the diagonal. And then everything off diagonal is 0. So we could also do like a 3 by 3 if that makes it a little bit clearer. It's just the diagonal has ones. And then off diagonals are 0. And so if we multiply this first equation on both sides by this, we end up with the second equation. And that is how we can easily get to the result of the inverse of this matrix. So the equation for this, which many of you mentioned earlier, so thank you for discussion. So we're using what this is also the determinant. If you guys don't know what a determinant is, it doesn't matter, but it's just equal to this equation here. And then what we're doing is, I guess it's not a super clear mapping. We're swapping the on diagonal value and then inverting or taking the negative of the up diagonal value, but this isn't like a closed form. A lot of times you'll just have a computer do these inverses for you. They're actually surprisingly difficult, especially when you get to larger problems. But this is just the equation you want to use for it. So just follow this or ask a computer to do it for you, because there's whole fields that revolve around trying to numerically take the inverses of matrices, because the closed form of like trying to extend this formula here to really large matrices is just computationally too intensive. It would take like if I have a 100 by 100 matrix, it would take ages to run through that. So you normally will do some numerical methods to try to speed it up. Yeah, and this equation is only for a 2 by 2 matrix. It's not exactly the same form for higher dimensional matrices. But feel free to look up. Like it's pretty straightforward to get to a 3 by 3 from this. But like 4 by 4 and larger is just like it's a lot of math. So now we want to use this formula to get our inverse of our Hadamard gates. So what we're going to do for that is we're just going to follow this exact formula, and I'll run through it for you. So we know that our inverse is, or I'll write out everything more explicitly, I guess. So we have 1 over our AD, which is just -1, minus, I always draw things too close together, minus our BC, which are these two terms, and that's just 1. And then we have our matrix where we take this D here is now up here. We have our B and C are the same but negative. And then we have our A is now in the bottom corner. And then we have our normalization still on the outside. We don't have to deal with it because it's just a scalar multiplication. You don't, so the reason why I always take the normalization out is because it's a scalar. And so if I don't have to deal with it, I don't want to. And a scalar will never multiply by a different number on different values of your matrix. It always multiplies every single element of the matrix by that same number. That's just how a scalar works. So you can very easily just remove it from your matrix for every operation you want to do. And so this results in us getting 1 over 2. Is that what I'm supposed to get? Let me think this through. Yeah, I should definitely get a root 2 out in the end. But let's just work through this and see where, and I'll figure out where I've messed up at some point along the way, hopefully. We have -1, -1, -1, 1. Yeah, I don't know if I should get this -2 out. I think it's written. Yes, this is actually, oh, you're right. This is a -2. So this is actually inverting all these guys. But then I don't know why this extra half. It's like, what? I don't know why this extra factor of 2 in the end. But I'll think about that while we go through it. It is just a scalar multiplication of everything, but we shouldn't be now getting half of what we had previously, because this is normalized. So this should be giving us just one. Oh, actually, maybe I do need to keep this inside of it. I might need to deal with this. Oh, yeah, I know what I did wrong. I have to deal with it when I'm taking this as, no, that doesn't fix it. This doesn't fix anything. No, oh, no, it does. Okay, there we are. This needs to be, because we're taking these bits as scalar values rather than as the entire vector. If we want to keep this normalized, we need to include the scalar multiplication on this. So this, you have to keep your scalars. I was just trying to be lazy and not do that. And then the result of that is we get -1 out, and then this all works out. So this just gives us our square root 2, and then we have negative values on the rest of this. Great. So yeah. Now, see, we got the right value out now that I fixed it. And we can use this matrix to give us what value we should get out for our initial question, what we were originally trying to ask. So would anyone like to try their hand at doing this math? I've already proven that I'm not always perfect with doing matrix multiplication. I'll give you guys a second to think about it, and then I'll go through it. I know we're a bit over, so I'll try to keep it quick. And this is just the same multiplication as we did before. Gotten one answer. And it's just because we're quite over time. I don't want to make you guys go through it, but if you get the answer, feel free to still let me know in the chat, even if I've already started working through it. Thank you, Elon and Avijit, for your responses. So what we want to do is just do the same multiplication as before. We're going to do the square root 2 times 1 plus root 2 times 1 over negative root 2 times 1 minus negative 1 over root 2 times 1. And then that's multiplied by the 1 over root 2 as usual. And this results in us getting 2 over root 2 on the top and 0 on the bottom. We then divide by this 1 over root 2, and that then gives us 2 over 2 or 0, which is just 1, 0. Wait. I should have a negative sign on this. It's like, wait a second, I did this completely wrong. This should be negative, and this should be positive. Sorry for that being really poorly done. It's the end of a day. Okay. Yes. So this gives us a 0. This gives us the root 2 or 2 over root 2. And then we do the exact same thing. It's sorry if this has been more confusing than it should have been. Just if you follow the procedure and you don't do it backwards like I did, then you won't have this issue. But we just get 0 over 2 over 2, which is just 0, 1. Okay, sorry for backwards. I had a big presentation early today and I haven't slept in a few days. So hopefully next week I will be making fewer mistakes. But again, it is like really easy to make a lot of these mistakes. It's all a matter of zeros and ones and negatives and positives, and it's really easy to just invert things like that. So great, now I've done a inversion of the matrix, and that is the end of the content today. If you guys have any questions, I'll stay on for a couple more minutes to go through if you have any, but you're all free to leave. I'm sorry for going so over time. I just wanted to make sure we got through all the content. Great. Okay, You guys are all so sweet. Thank you. I will hopefully get some sleep very soon after this. But I've gotten a question from Mo about this this inner product. And yeah, so the notation we use was that we have the conjugate of the second matrix or of the first matrix in the multiplication. This is all dependent on your on what you want to get out. But yes, if you the generalized form is with the conjugate of B. Okay. 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 Well, thank you all for attending lab. I hope you got something out of it. I'm sorry for going so very over. But yeah, I think it's the end of lab. Okay.
All right, thanks everyone.
Thanks everyone.